Hey guys, chapter 6. So chapter 6 is about applications of definite integrals. We already saw application of definite integrals in terms of computing the area between the curves, or computing the average of the function, and so on and so forth, right? So in here I will only cover 6.1, so which is about computing volumes, not areas, so volumes, using cross-section. So learning objectives are, so we consider slicing by parallel planes. Then we introduce two methods, so the disk method and the washer method. These are helpful when computing the volumes obtained by revolutions of two-dimensional regions. So let's get started. Slicing by parallel planes. What is a cross-section? Well, cross-section of a solid is the planar region formed by intersecting S with a plane. So you sort of cut your solid. What is a solid? Solid is a three-dimensional object, right? So you cut it out in some way with some place, and whatever uh, region is cut it out, that's called the cross section. So here the cross section would be this small piece of the solid, right? So let's say that the task here is I would like to calculate the volume of this solid from restricted from A to B, right? So what I do is, as before, I'm going to consider the slices, right? So now in this case, I'm not slicing with lines, but instead I'm slicing with planes, right? So I will be slicing with planes, and then I need to obtain a area, right? How am I going to obtain area? Well, first we need a volume formula. So let's say that I sliced, and this is my cross section, right? And then if you thicken in, let's say, that vertical direction, there it will be like a horizontal, but anyway, so if you thicken it, you will get a shape of this form, right? And this thickening is, let's say that the height is equal to h. Then the volume can be calculated as the base area, so area of this cross section multiplied by the height, right? So this is how we calculate these small pieces of volumes, and then summing up all these small pieces will give us volume of the solid at the end. Okay, so let's set up this Riemann sum, right? So as we said, so let's say we have an interval from AB. You look at this partitions, right? So you slice your regions by these planes, and then you what do you do? So you pick any sort of x in here. It could be just an endpoint or whatever. So then what we need is we need to calculate this volume, right? So let's call it sort of delta vi for the ith interval. So what is this? This is roughly the height. So what is height here? It's delta x, right? So here it's denoted by k. Okay, we can also denote by k. So let's get vk. So here I'll get this area. Let's call it a with respect to xk, or we can k star, right? If you pick some point inside of this interval. So that's my area. I multiply by the height, which is delta x k, right? So this width of this interval, that's going to give me the volume, the one small piece of volume. Then how you get the whole volume is going to be roughly the sum of these small volumes. So a xk delta xk, right? Where k runs from 1 to, let's say, n, and then you let n go to infinite, which will give you the integral formula, right? So the volume of a solid, but integral cross-sectional area. So my function is ax, so you see I'm thinking my a as a function of x. So if you manage to calculate this ax, you multiply by delta x, which is the thickening part that gives you the volume, and you integrate from a to b. That will give you the volume of the solid. So the process of calculating the volume is as follows. So first you sketch the solid and the typical cross-section, right? So visualization is important. And then next is you find the formula for AX, right? The typical area. And then find the limits of integration, AB. And finally, you simply integrate AX from AB. Let's do an example. All right. A curved wedge is cut from a circular cylinder of radius 3. So we have a cylinder, right? And it's cut by two planes. So one of them is XY plane, right? The space one. And the second plane crosses the first plane at 45 degrees. So there is a 45 degree, right? This upper side is cut by a plane that's has an angle 45 degree. So we'd like to find the volume of this green region. Alright, so this is a solid. You can consider various cross sections, right? For example, you can consider cross section that's parallel to xy, right? XY plane. That's possible. However, you should be able to calculate the area, right? So as far as you can find the area formula, that's doable. Another option could be you cut with perpendicular planes, but let's say parallel to x-axis, right? But then again, you need to know how to calculate the cross sections. I think then cross sections are going to be like trapezoid, and if you can manage, it's also doable. But I'll follow the method done in the book, so which is you cut again with perpendicular planes, slice with perpendicular planes that are parallel to y-axis. Then, as you can see in the picture, we will get nice rectangles, right? So finding the area of a rectangle is not so hard. Well, because it is 45 degree, if I denote this part, this x-axis x, then height is also going to be x, right? This height is also going to be x. Oh, great. So we already know the height of this rectangle. Now we need to know the width, right? So if I manage to find these 2 points, I'm done. But what is this? So this huge thing, this is a circle, right? This is a circle of radius 3. So I know that all the coordinates in this circle satisfies x squared plus y squared equal to 3 squared, right? This is the formula for the circle. And at this point, I know my coordinates, and at that point, my coordinates are x, right? This is x. So then my y coordinates are 9 minus x squared in square root, right? This is plus minus. So along y-axis, so here I'm going to be, this is negative, here that is positive, right? So once I subtract the two, then the width of this rectangle is going to be 9 minus x, square root of 9 minus x squared minus square root of 9 minus x squared. So it's 2 times 9 minus x squared. So this area formula in terms of x is 2 times square root of 9 minus x squared. So that's kind of the width, and then multiplied by the height of this rectangle, which is x. Okay, so this is just an area. And then we have the thickening. How are we thickening? Well, we're cutting along the x-axis, right? So thickening is going to happen in x direction. So it's going to be delta x. Hence, the volume formula is going to be integral from this point to the end point of the cylinder, which is from 0 to 3, and then the area is 2. Let's bring x to the front. Square root of 9 minus x squared dx. Right, so how do we handle the integral? Well, we can make a u substitution where u is equal to 9 minus x squared. Then du will be minus 2x dx. So we already have 2x dx. Hence, the integral is going to be minus square root of u du. We can also fix the limits. At x equal to 0, u is 9. At x equal to 3, u is 0. So if you like, you can flip the integral and forget this minus sign. So you can do from 0 to 9, here u to the 1/2 du. Integrating gives you u to the 3/2 divided by 3/2 from 0 to 9. So this is 2 over 3 times 9, 3 over 2. Well, square root of 9 is 3, so this is 27. So 2 over 3 times, I guess this is 27, so they cancel out. 9 times 2, this is 18. Right. Now, often we might have a problem where we want to find the volume that's obtained by revolved some sort of a region. So typical region could be something like some function here, right, curve, and then you restrict yourself to x-axis from A to B. So this is your region, and then what you do is you revolve along x-axis, right? So you revolve along x-axis, you revolve, you obtain a region, something like this, right? With some revolutions, right? So here, some revolutions, etc. Right? So a region revolved. So the interesting question is, how do we find the volume, right? Well, again, you apply the same approach as it's done. Look at a cross section, right? Look at the cross section. What do you get? Well, because it's just a revolution, right? So you basically here for this particular cross section, you basically pick this segment, right? It's fixed. You rotate, right? So then you get a circle right here, right? This is going to be a cross section with circle. So this area formula for the circle, it's easy, right? It's pi r square. But what is r? R is right. This is my r, right? This y axis is my r, which is governed by f of x. So then this is going to be pi times f x squared, right? And then you make the thickening, right? You make this thickening along this x-axis, right? So this is going to delta x. So then this small volume, right? So this small volume is going to be pi fx squared delta x, right? I mean, what is it I'm getting? This is roughly. So what this is just the volume of this cylinder, right? Then the volume can be obtained simply by the integral, right? So ax is equal to integral from a to b pi rx squared dx. So what is this r? This r is exactly what I take as my function f, right? So that's the radius. All right, the region between the curve y equal to square root of x restricted on 0, 4 interval and the x-axis revolved about x-axis to generate a solid, right? So you need to sketch the graph of y equal to square root of x, restrict yourself from 0 to 4, rotate around x-axis, right? So this is my function right here, and then when I rotate, I get some solid of this form, right? And I would like to calculate its volume. Well, again, first we need to find the area. What is this? This is pi. So let's use the same notation as in the previous previous slide's formula. So Rx here, my Rx is, this is the radius, right? So what is the radius at x? Well, the radius is governed by y-axis, so this is square root of x. So this is going to be pi square root of x squared. So this is simply pi x, right? Hence, the volume, so the volume is going to be the integral from 0 to 4, right? Because I'm slicing along x-axis, but x-axis ranges from 0 to 4, so it's integral from 0 to 4 pi square root of x squared is x times dx. This is the thickening part, and that gives us the volume. So what is it? Pi x squared over 2 from 0 to 4. So at x equal to 4 is 16 over 2, so this is 8 times pi minus 0, so 8 times pi. Alright, another example, a bit more involved. Find the volume of the solid generated by revolving the region between the parabola x equal to y squared plus 1 and x equal to 3 about the line. So you see, I'm rotating about x equal to 3. I'm not rotating along the x-axis or y-axis. So it's different sort of a rotation. So I need to be a bit careful when it comes to finding the area formula. So here is the figure. So my parabola x equal to y squared plus 1 is on a blue curve, and x equal to 3 is my red, right? And then I'm rotating around this x equal to 3, right? So, and then what do I get? What do I get? As a result, this is the shape I get, okay? And then I want to calculate the volume. How do we do it? Well, now if I cut it along x-axis, I'm not getting circles or the discs, right? But if I cut along the y-axis, right, the parallel planes to the x-axis, so then I'll get these nice discs, right? So we do cutting along the y-axis. Well, what do I get? So let's look at this particular one. So let's cut it at y, right? At y, and then try to find this radius. How do I get the radius? Well, what is the radius? Well, it's nothing but the difference between these two x-axes, right? So here this is 3. I know this is 3. How about this particular one? What is the x-coordinate? Well, x-coordinate is y squared plus 1. So then my r, y, right? Because I cut it at y, so this is a function of y. This is the 3 minus this particular x, which is y squared minus 1. So this is 2 minus y squared. So this is my radius. Hence, the small area is going to be pi times 2 minus y squared. Hence, the small volume is going to be pi squared 2 minus y squared times delta, not x, delta y, because I need to thicken along y coordinate, right? Very nice, very nice. Well, what next? So then the volume is going to be an integral of this expression pi 2 minus y squared here is going to be dy. What are my limits? Limits are they given? It's not given, right? The limits are not given. So because I'm slicing with horizontal lines, I need to look at the limits along this tip, the y coordinate of this tip and the y coordinate of that tip, right? So how am I going to calculate it? So what is this? This is the intersection point of this so parabola and this x equal to 3 line, right? So you equate the two. Let's calculate it here. So x is equal to y squared plus 1. This must be equal to 3, which means y is equal to 2. Y squared equal to 2, which gives me y equal to plus minus square root of 2. So hence the limits, right? So the limits runs from minus square root of 2 to square root of 2. Right. How am I going to integrate 2 minus y squared? Well, all you have to do is simply go ahead and expand it. So if you expand the term, what you get? You get 4 minus 2 times 2, 4 y squared minus plus y to the power 4 dy, right? And then what is this? Well, if you integrate, this is here we get pi 4 times y minus 4y cubed over 3 plus y to the 5 divided by 5 evaluated from radical 2 to radical, from minus radical 2 to radical 2. Right, so I'm not going to evaluate it, so I'll leave it as an exercise if you want to try and find the volume. It needs to be positive, right? Okay, so the last topic for today is the method of washers. So what is it different from the previous one? Well, let's look at the following. Let's say that I have a region, this blue region, that's restricted between two curves, capital R of x and little r of x. Okay, and then what I do, I rotate this region along x-axis, right? So if you rotate this particular tip, you will get something like this. If you rotate that particular tip, you get something like this. So this part will be filled in, but this inner circle will not be filled in, right? So that kind of shape is sort of called washer. So once you make this revolution, here what you get, that's the solid you get. As I said, I mean this part is left out, so it's not completely filled, right? And then the question is, how are we going to find the volume? Well, how do you find the volume of, let's say, a donut or something? So write this part, this washer. Well, what you can do is you can calculate. So this is area formula, right? A of x. So you can calculate the whole disk, right? You can calculate the area of the whole disk. What would that be? That's going to be pi capital R square, right? This is radius is capital R. And then you calculate the area of this small circle, which is little pi little r squared, right? It's coming from here, right? If you subtract, you will get this red shaded region, right? That's it. So then the integral becomes as follows. So your ax is pi rx squared minus r little rx squared dx. Right? So this is called the washer method. Let's do example. All right. So we have two curves, x squared plus 1, a parabola, and minus x plus 3, a line. And there is a region that's enclosed, right, bounded by this. So we also need to find where they intersect. But anyway, then we go ahead and revolve it, right, along x-axis. So that's the solid you get. Again, as you can see, there is a hole inside. So we'd like to find the volume of the solid. Again, if you look at the cross section along x-axis, you see this shell, right? So I need to find the capital R, the upper radius, or outer radius, if you like. What is it? This is governed by this equation. So this is minus x plus 3, and then the inner radius is governed by this parabola. So this is x squared plus 1, right? Great. I also need to decide for the limits, right? Where am I going to integrate? Since I'm slicing along x-axis, I need to find the bounds for the x, right? Well, these are the intersection points, so I need to equate the two. So I say y is equal to x squared plus 1 is equal to minus x plus 3. That gives me x squared plus x minus 2 equal to 0, which I can write at x plus 2 x minus 1. That's equal to 0, gives me x minus 2 and x 1, right? So basically what I have is here I have minus 2, here my 1. Hence the volume is going to be the integral from minus 2 to 1. I can take out pi if I like, and here I get capital R squared, which is minus x plus 3 squared, minus little r, which is x squared plus 1 squared, multiplied by the thickening dx, and integrate. That's all, right? So let's see what we get. Minus 2 to 1. The square of minus x plus 3 is x squared minus 6x plus 9. X squared plus 1 squared is x to the 4 minus and minus 2 x squared minus 1 dx. So I have minus x to the 4, x squared minus 2x becomes minus x squared minus 6x plus 8 dx. So once you integrate, you get minus x to the 5 over 5 minus x cubed over 3 minus 6x squared over 2 plus 8x evaluated from minus 2 to 1, which gives us 117 pi over 5. Alright,